Emma. Calorimetry is measured with a calorimeter. That's your vocab term. A calorimeter is an insulated device used for measuring the heat absorbed or released during a chemical or physical process. Now, I want to make sure you guys understand the difference between absorbing heat and releasing heat and what that would feel like. So I want to talk about heat absorption. So I can stop writing in red again. Let's go back to this. Heat absorption. This is going to be very important. If you can understand this and grasp this, the rest of the unit should be made a whole lot easier. The other day, somebody put some sort of headache relieving topical ointment. Topical means you can put it on your skin, on the back of my neck, and it got really cold. It got really cold to what I was feeling. Now, you need here. Yesterday, I told you how to think about the flow of energy from both perspectives, like winning and losing. The Bucks won because the Chiefs lost. Things like that. Your mom gave you 20 bucks. You just got $20 richer. Your mom is now $20 poor. If I put this thing in the back of my neck and it's feeling really cold, to me, is it absorbing heat or is it releasing heat? It's absorbing. So if you were to touch something and it feels cold, it is absorbing heat. That is heat absorption. It's going to be cold to the touch. When you touch ice, what do you think is warmer? You or the ice? You would be. And what way does heat flow? Warmer object to cooler object or cooler object to warmer object? Warm to cool. Clearly, you, mammals, all of you are mammals, you have warm blood, you are warmer than an ice cube. And so if an ice cube is in your hand and you feel the ice cube cold, is the ice cube getting warmer or cooler as it sits in your hand? Where is that heat coming from? It is coming from you. And so the ice cube is absorbing heat. Now, if we could talk to this ice cube and it could actually form words, we place this ice cube in your hand, how would the ice cube describe how you feel? You would feel warm. And so when it comes to heat releasing, this is going to be warm to touch. If you can get that sorted out, you'll be able to go a long way in figuring out which way heat is flowing. Is it being released or is it being absorbed? Some of you are driving now. Let's say you drive from Tampa to St. Pete, you drive back, pretty decent drive. You put your hand on the hood of your car. The hood of your car feels very, very hot. Is your car absorbing heat or is your car releasing heat? It is releasing heat. So how does it feel? It feels hot. But if you touch something that feels ice cold, it is going to absorb heat. That's how it works. All right. A calorimeter is able to gauge like how much heat is being absorbed or how much heat is being released. So let's do an example. You might see this on your test. You might see this on your review. I have a glass, and this glass is water. In the glass, I place a raging hot piece of metal. This metal is really hot. Which way will heat be flowing? Into the piece of metal or out of the piece of metal? Out. Heat will be flowing out. When will this heat flow stop, Arshan? When they have reached or achieved equilibrium. So in this example, a very hot piece of metal is placed in a glass of water. Heat flows from the metal to the water. So as this goes on, what is happening to the temperature of the metal? Is it increasing, is it decreasing, or is it staying the same? The metal is going to decrease in temperature. What will happen to the temperature of the water as this continues? The temperature of the water will increase. As Arshan said, this will stop. Both are at the same temp. This is called equilibrium or balance. Your ice, if you put some ice cubes in your glass of water, the ice is going to melt and it's going to warm up the water until everything is the same temperature. All right, let's move on. Let's go to another example problem. Very similar to what I just said. You ready? A piece of metal with a mass of 4.68 grams absorbs 256 joules of heat when its temp increases by 182 degrees Celsius. What is the specific heat of the metal? Okay, this is a problem that we did yesterday with specific heat. Do any of you recall, without looking at your notes, now it is far from your test, but if you've memorized this already, that'd be great. Do any of you remember what the equation is for calculating specific heats? Besides Arshan, he was quick to raise his hand. Go ahead, Kevin. C times M times delta T. So we're all clear. What does Q stand for again? What is heat measured in? Joules. What does M stand for? Mass. What is mass measured in? Grams. What does delta T stand for? Delta means change, temp means, or T means temp. That's going to be in Celsius. How do you calculate the change in temperature? Final minus initial. And what does C stand for? Do you remember how to say the unit of measurement for specific heat? Joules per gram per degree Celsius. It looks like joules over grams times degree Celsius, but the way that you say it is joules per gram per degree Celsius. Okay, so let's see if we can identify which variables we're given. Nick, can you read this problem and tell me one of the variables that we are given a known value? 256 joules. Okay, 256 joules. What variable is this? Q. That is Q. Good. Max, can you tell me another variable that we are provided in this problem? 4.68. 4.68 grams. What is that going to represent? That is correct. And Scout, can you tell me what is the third variable that we are given in this problem? Is it the temperature or the change in temperature? Yeah, it says it increases by that much. So that's going to be delta T. So what is our unknown value here, Tim? C. What does C stand for? Specific heat. And it's going to be an unknown number of joules per gram per degree Celsius. All right, so I think you guys know how to rearrange this algebraically. You did something almost identical to this yesterday. If you actually show your work, you got Q equals C times M times delta T. Juliana, how do we isolate C so we may solve for it? We need to get this little guy all by itself. You divide mass on both mass and change in temp on both sides. Good. So those cancel out. So if I were to clean this up, it's going to look like this. Okay, guys, you were asked to bring your calculators every day. I hope you got them from your sister. All right, so solve it, por favor. Let's find out what the specific heat is. I'm going to give you guys a chart. I know those of you online will not be able to see this chart, but I would provide it. I'm going to ask you guys, what type of metal is it? So I'm going to show you the chart. You can refer to the chart. Yeah. If it releases that much, then it is a negative value. That's called ectothermic, and it's negative, and endothermic is positive. Yes. It died again. I've heard that from you before. Get it resolved. Use your phone. You need to get your calculator fixed. You guys have this yet? What is C? 0.289. I have something different. We have, yeah, I got 256 joules. If you're leaving now, don't forget this will be on YouTube. 4.68 times 182 degrees Celsius. What? It's not, I'm just going to show it. I'm not going to pass it out. What is the answer? 0.301 joules per gram per degree Celsius. Okay. So let me show you my chart here. I want you guys to tell me if you can see what element are we using. Strontium. Answer strontium. You see the specific heat is 0.301. I would give you this chart. So if I gave you this problem, I said, okay, what is our mystery element? All you would have to do is take this number, 0.301, and just look at the chart and find out what has a specific heat of 0.301. Now, riddle me this. We talked yesterday about the biological implications of water having a very high specific heat. Its value is 4.184. That's really, really high. Strontium is 0.3. Can that absorb a lot of heat before it starts changing temperature? No. Strontium is going to start changing temperature immediately. And it's going to be really, really hot if it's exposed to hot temps, unlike water. All right, let's keep going. Yeah, now we're getting into the good stuff. We might actually get to section 3 today, which is good because this is a very big unit. Let's talk about chemical energy and the universe. Sounds like we're getting all philosophical. Every chemical reaction either releases or absorbs heat. You just have to determine which one it is. Remember, if something is cold, what is it doing? It's absorbing heat. And if something is warm, it is releasing heat. So here comes the main term of this entire unit. This is known as thermochemistry. That is the title of this entire unit, and that is yet another vocab term. Thermochemistry is a branch of chemistry that is the study of heat changes that accompany chemical reactions and physical changes. When I say physical change, what is the chemical formula for ice? Yeah. What is the chemical formula for water? And what is the chemical formula for steam? It's all H2O, isn't it? But let me ask you this. When you go from liquid water to steam, is that heat being absorbed or is that heat being released? To get liquid water to become steam. It's absorbed. What about getting steam to become liquid water? It's released. How about ice to become liquid? And liquid to become ice? Released. It's a cooling process or a heating up process. All right. Well, in chemistry, we have three facets of how heat is exchanged. We have the system, we have the surroundings, and we have the universe. The system is a specific part of the universe that is experiencing, that is either absorbing or releasing heat. It's a specific part of the universe that contains the reaction or process you wish to study. So what I like to say is that the system is what you're focusing on. If I'm holding an ice cube in my hand and I want to see what the heat flow is, the ice cube is the system. Or excuse me, the ice cube is the system. The surroundings, we're getting a lot of vocab done on these 3 days so far. The surroundings is basically everything else in the universe. So anything that you're not focusing on is the surroundings. And then the universe is just the system plus the surroundings. So I'm going to give you guys a little drawing here. Let's say I want to find out how much heat is either entering or exiting this experiment. This right here, this would be the system. Next. Everything else this is the surroundings. Imagine the system loses heat. Where is that heat going? The surroundings. And let's say that the system is gaining heat. Where's that heat coming from? Right. So this goes back to the first law of thermodynamics. Heat cannot just be created or destroyed. It has to come from somewhere and it has to go somewhere. It doesn't just get poof created and it doesn't go out of existence. It all comes from a source. When you get your $20, it didn't just miraculously appear in your hand. You had to go to mom to get it. Oop, made that square a little too big. So what do you suppose the universe is? Any ideas? Look at the definition. What? The entire box and everything in it. So what is the net change in the universe? 0. There's no change in the universe. It's just flowing from one area to another. Within the universe, no, but to different parts of the universe, yes. You know, imagine, Arshawn, that your dad gives you $20 inside your house. The $20 were from you to, or from him to you, but in your household, the $20 still stayed there. It's just going from one part to another. All right, so system plus surroundings equals the universe, okay? Any questions so far? All right, let's keep on going. Let's get to a new term here called enthalpy. The symbol for enthalpy is H. And it is the heat content of a system. So to consider with enthalpy, pressure is constant. So it's going to be a non-factor. What we're going to be doing in here is we're going to be calculating the enthalpy or the heat of a reaction by finding the change in the reaction. So we're going to find the delta H of the reaction. Remember that RXN is just an abbreviation for reaction. Now, if I want to find the change in enthalpy of a reaction, just pretend it's like the change in temperature. When we were doing the specific heat equation, how did we find the change in temp? What minus what? Final minus initial. So how would you find the change in enthalpy? Final minus initial. The change in the enthalpy of a reaction is going to be the change in the final. Oops, that shouldn't be a triangle, just H. Minus the enthalpy at the initial stages of a reaction. Final minus initial, every single time. This is how you're going to be able to calculate the change in enthalpy of a reaction. Now, something to keep in mind. If the change in enthalpy, which would be delta H, is negative, do you think this would indicate that heat is being lost by the system or heat is being gained by the system? If you were losing blood or you were losing money, let's say you're losing blood, are we going to say that is a positive or a negative? Is that a gaining or a reduction of blood in your system? It's a reduction. And we would always calculate a reduction as a negative. If you just spent $50 at Chipotle, if you are able to open up your bank account app, you go to your checking account, it's going to have $50 there, but is it going to say positive or negative? Negative, which means did you just spend $50 or did you just gain $50? You spent it. That's simple accounting. Well, when it comes to the accounting for chemistry, negatives mean a loss. Same thing as banking. And positive means gain. So change in enthalpy is negative. It's energy lost. And vice versa. If the change in enthalpy is positive, it's energy gain. Okay? So what we're going to be doing now are things you guys have done already. We're just going to incorporate heat. This is going to be kind of like Unit 8, but with a twist. Unit 8 was when you all learned how to read a chemical reaction. This is going to be that same thing, but we're now just accounting for heat. All right? So let's consider this equation. And it is balanced. Okay. I want to see if you guys can actually say this properly. Is there anybody that thinks they have the gumption, the courage to say this entire equation, including the coefficients? Who's got the courage? Arshawn?
4 iron.
You say 4 moles.
4 moles of iron plus 3 moles of oxygen gas. No, react 3 moles of oxygen gas to yield 2 moles of iron free oxide.
Very good.
Plus 1,625 joules.
Okay. I want you to guys, this is going to be very important. You guys see joules now. This is the new twist I just referred to. Is joules a reactant or is joules a product in this particular equation? So does this indicate that energy is being lost or is energy being gained? Lost. I did not hear anybody say gained. Very good. Remember that products are sent out. In a few weeks, the seniors will graduate. They are the products of Plant High School. They're out the door. They're gone. They're never coming back. Reactants would be like next year's freshmen. They're coming in. So whenever you see energy as a product, this indicates energy lost. It's a dead giveaway. If it's a product, it's out of here. If one of you grows up to be a baseball bat manufacturer and you load up a truck with a bunch of bats that just got sold to Major League Baseball, those products, which is what you made, are gone. They're history. You lost them. They're out. Products are going to be gone. So is this entire process of iron and oxygen reacting to make iron 3 oxide, which is rust, is this an energy gaining process or is this an energy absorbing process? Or excuse me, gaining or leaving process? It's leaving. This is called an exothermic reaction. And then, hopefully you've heard of this before. What type of skeleton does a crab or a spider or a grasshopper have? An exoskeleton. And what does exo stand for? Outside. 1 second, answer the phone. Thorson. Yes, I do. Okay. Melissa, you can sign out. Tell your parents that if the test, we're not doing anything today. Hope not, because we are. You're responsible for what you miss. All right. So here's how this looks, guys. Here's how you actually write it, and you might actually see this on your homework. So you would put 4. Oops, wrong color. You put 4 Fe plus 3 O2. Whoop, why did I put parentheses there? And here's what I want you to realize. You said this is an energy leaving process. So let me ask you this. See if you might be able to figure this out. What has more energy? Ready? The reactants or the products? Considering heat left. The reactants have more energy than the products do. So you're going to draw, or you're going to write 2Fe 2O3 here. And I'm going to draw this arrow pointing down. This means, do you think that means energy loss or energy gain? There's an arrow pointing down, guys. I mean, come on. The arrow is pointing down. I only hear Arshawn talking. I want you to hear more of you. The arrow is going down, so that's energy lost. How much energy was lost? You're going to say that the change in enthalpy is what? Are you going to say 1625 or negative 1625? You're going to say negative 1625 joules. The reason why I drew the arrow going downward is because this reaction is losing energy. If you were actually to write this as an actual graph, that's my next lesson for you. The x-axis is the progress of the reaction. The y-axis is energy. Here's what you do. Watch this. Right here, at the beginning of the reaction, you have reactants. In this case, this would be 4Fe plus 3O2. Way down here would be products, and that would be 2Fe2O3. This reaction clearly lost energy. If you look at the y-axis represents energy. The higher you go, the more energy you have. The lower you go, the less energy you have. As this reaction proceeds forward, you can see, look here, and it has a little spike, which is just the reaction itself, and then the amount of energy goes down significantly. This is known as an exothermic reaction. That's what I'm saying for the phone ring. What does exo mean? Inside or outside? Outside. Exoskeleton. The word exit. We get the word exit from this. You have an ex-boyfriend or an ex-girlfriend or an ex-husband or an ex-wife. Ex. They're out. Ex means gone. This is known as an exothermic reaction. So what do you think a reaction that gains energy is called? Endo. That's where we get the word for enter. Endo. We have an endoskeleton. Our skeleton is inside. So I want to give you another equation here. Let's do this one. Zoom in a little bit. Yeah.
So is like every reaction of iron dioxide produce so much energy, or is that just that one? Like it's not every reaction.
I think that is accurate. When iron and rust, or when iron and oxygen react to make rust, it releases energy. I think that is the actual amount.
So it's still not like basis for basis, like every reaction has a
Mm-hmm. Okay, guys. Is this reaction I just wrote endothermic or exothermic? Endo. So what has more energy? This is where I think you're going to get a little brain twisted. Your brain is going to tell you one thing, but your instinct's going to tell you another. What has more energy? The reactants or the products? Right. That energy that's on the reactant side. Here's what the untaught person would think. I see 27 kilojoules on the reactant side. Clearly, the reactant side has more energy. No, 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 no. That energy is going into the products. And so that's going to make the product energy level higher. Good. So here's how we would write this. We have NH4, NO3. Where am I going to write the products? Above that or below that? Above. I'm going to write it like this. NH4, and NO3, ammonium and nitrate, and I'm going to have an arrow pointing up. How much energy was gained here? What's the change in energy? Would that be positive or negative? Now, you don't have to put a plus 27, but I'm going to do it just so everybody's clear. That's going to be an increase, which would be a gain of 27 kilojoules. How many regular joules is that? 27,000. Right. So
Mr.
what
Thorson?
type of reaction is this? This is known as an endothermic reaction. Now let's put it on a graph. X-axis is the progress of the reaction. Y-axis is energy. Here's my reactants right here. This is NH4, NO3. Are my products going to be higher or lower than that? Higher. It's going to look like this. Here's my products. NH4 plus NO3. So the products clearly have more energy. Now, how much did it increase by? If I go from here to here, guys, check this out. How much did it increase by? Tell me again. This increased by 27 kilojoules. That's right. The what? That's the enzymatic reaction. You haven't learned that yet. I'll explain that. Arshan's asking, what's that little like bump up there? That's the enzyme. All right. Let's see what I want to do here. Tomorrow will be a short day, or we can actually do what I want to do tomorrow, or today, tomorrow. So we'll stop here.
Mr. Thorson,